So, Assalamualaikum warahmatullahi wabarakatuh. Uh, Good morning and good day, good afternoon, good evening for everyone that watch my video in here. So, I want to present my research about fault delineation on seismic 3D prospect data using artificial intelligence. First of all, I want to know to inform you about my outline in this presentation. In the first part, I want to talk about the introduction, and the next is CNN and data augmentation and training phase application, and the final is the conclusion. For the first, let's move to introduction. So, one of the challenges faced in oil and gas exploration using basic data is related to delineation of fault in seismic data, where fault themselves are one of the geological features that are quite important in exploration because they can indicate possible hydrocarbon migration pathway and important structural traps. Usually, fault appear as a factor that have discontinuity laterally. Therefore, some seismic attributes, such as variance, semblance, or curvature, can identify faults, but these attributes only show symptoms of fault and cannot automatically picking fault. So, in this research or in the study, I use deep learning algorithm, especially convolution neural network algorithm, because the algorithm can we teach about anything that we want to uh, accomplish. Like if we want to detect fault delineation, so we have to the data and the pair of data, so the seismic data and the fault itself. So for this reason, the authors choose deep learning algorithm to identify the fault on post-stack 3D seismic data to address a challenge in the fault identification process, which is notoriously time-consuming and also highly dependent on the paper skill. Even though it has been carried out by previous researchers, this algorithm itself still has many variations in its application, so it is felt that it is still necessary to explore the variation to identify faults in seismic data. Thus, deep learning is expected to be a substitute for the manual fault identification workflow and switch to using the algorithm which is automatic. And the purpose of this study is how to make the resulting delineation very accurate and have a high resolution so that the interpreter can perform fault picking without any hesitation. And also, this research is limited only to focusing on synthetic data and not focusing on field data. So it is uh, the first uh, experience to me to research this field of study. So let's move to the CNN. So the basic concept of CNN is actually a combination of input data given a non-linear function. This linear combination will be given one parameter in front of which is named weight or uh, weight itself. So in here we have a picture to describe the algorithm itself. So in here we have an input x1, x2, and xk, and we have to do a linear combination for x1, x2, and so on, like this equation in here. So I uh, point in this equation. So in if you see this, we have a weight in this. We have the first weight, the second weight, the third weight, and the fourth weight. So there is the simple explanation about the algorithm. So the INN or artificial neural network consists of two parts, namely feed forward and back propagation. This back propagation will fix the weight value according to the input you want. The changing this weight value until it fits the data. It's called the learning process. So the process of the updating the weight is like a uh, the inversion of the physical data. So in the next iteration, and then the last iteration, uh, the weight is always updated until it is fit to the input and output of the data we want. So previously I mentioned about the activation function. So this is the activation function uh, in the CNN or any development client. We have sigmoid, anha, relu, leaky relu, max out, then and relu. So bit propagation is carried out with an optimization algorithm similar to the process in geophysical inversion, just like I mentioned before. Next part is data augmentation. So the initial data set is 200 pairs, and the augmentation was carried out with the benchmark of the time depth direction, so that the data use amount to 800 pairs of the data. So the data is the rotate in the time depth direction like this. If you see, so it is rotate for the 90-degree. So it is the original seismic time slice. So this is the time slice for the 90-degree. So the time slice for 100, uh, 180 degrees. So uh, 270 degrees. We have so the augmentation is done by 2 by 4 direction itself. So we have 200 pairs of data. So we have 300 pairs of data. So this so the augmentation purpose is to 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 outnumber the data itself and enrich the, the fault itself. So this is the training phase. So this is the architecture that we used in this study. So if you can see, this is have a double convolution plus review, and then we go to the downsampling test, and then do the double convolution again, and the upsampling. So we have the final output, the output fault image probability between 0 and 1. So this is the result of the training test. So the training process is carried out using the NVIDIA RTX 3060 Ti GPU. Each training process is carried out in the each batch where the size of each batch consists of 2 pairs of the data. And the training process itself, the Adam optimization method is used when the learning rate is 1e minus 5. So the time needed to complete 1e of the aforementioned computer specification is approximately 156 seconds. So the training time in at the 9 epoch is approximately 231 minutes. So if you see, we have 3 data picture in here. So in the first picture, I point this is the cost value change related to the info. So this is show about the training process itself. So it is good or not. So if we have the convergence score like this, so the training is good. And then for the metric we use, we have this precision F1 and recall. So in here too, the metric, the metric variation with the epoch itself. So if it's the best value of this metric is 1, so we have all metric in this in here approximately to the 1 value. So this is the application of the my model itself. So in here we have the we have the in the first row of the picture in here we have the original seismic, and the second row we have the ground truth of the label of the data or the fault, and then this is our CNN model prediction about the fault, and the last row in here I point this is the another method to detect the fault to name variance. So if you see, our model is very clean, do the very clean prediction about the fault, and all the fault in here is defined uh, continuously, and all is the accurate, and resolution is very good compared to the variance in here. So we have, if you see the white uh, color in here is the prediction tool, but there is so many noise in here, and we have the uh, so the variance to give a delineation like this, but it is not a continuous delineation. So it is my our model is outperform the variance. So in the two, just like the previous result, but in the another seismic data, seismic synthetic data, seismic synthetic models. So just like I mentioned before, the position of the picture, just like the previous slide. So, and this is the 3D visualization about the prediction of the delineation, but it is just for my our CNN model that passed the training phase. So if you see, this is the discontinuity. So we have the discontinuity in here. So if I to the next slide, all of this discontinuity is defined well in the 3D data. So in the end, the application of convolutional neural network algorithm using the 3D linear architecture modified in terms of loss and data scaling technique to the linear fault. Interesting data has been shown to be able to estimate the presence of geological feature in the form of fault in the seismic data held on synthetic data. This is evidenced by the level performance of the training and test data that has been received from the CNN model, which has gone through the spatial training step using the synthetic data, which is quite good, namely the loss function value for the extract and test that have converged at value 0.0154 for the train and 0.0308 for the test in the 1989 epoch. Meanwhile, based on the qualitative assessment of the three performance metric measured, the ideal value were received, namely precision, default, and F1 is receiving the ideal number for each performance metrics too. So it's the end of the presentation. I hope you understand all of the explanation. So thank you for the attention. Assalamualaikum warahmatullahi wabarakatuh.